Good morning students, welcome to Lakshya Academy YouTube channel. Up to now we discuss the concept of semiconductors and the types of semiconductors. Once I brief the concept of semiconductors. A substance which has the properties in between the properties of conductors and insulators is called as semiconductor. In the case of semiconductors, a small energy gap lies in between valence band and conduction band, that is called forbidden energy gap. And in the case of silicon, the forbidden energy gap is 1.1 electron volt, and for germanium it is 0.72 electron volt according to NCERT book. When a small amount of heat energy is given, electron easily jump from valence band to conduction band because the energy gap is very less. The deficiency of electron in the valence band is called as holes. Hole has no physical significance, it has a positive nature. When small amount of energy is given, electrons easily jump from valence band to conduction band. So, the number of free electrons available in the conduction band increases, and the fraction is given by P proportional to exponential minus Eg by kBt, and this you learn in detail in electrochemistry part. Unfilled regions are termed as holes, and holes has positive charge carriers. There are two types of semiconductors, one is pure semiconductor and another one is impure semiconductor. Pure semiconductor is also named as intrinsic semiconductor, and impure semiconductor is also named as extrinsic semiconductor. First, pure semiconductor. Germanium and silicon are the best examples of pure semiconductors. Consider germanium, atomic number is 32 and its valency is 4. So, it means it is ready to form 4 covalent bonds with neighboring atoms. When small amount of heat energy is given, the covalent bond breaks and electrons easily jump from that valence band to conduction band. So, in the case of pure semiconductor, the current is due to both electrons and holes. And in the case of pure semiconductor, the number of electrons present in conduction band is exactly equal to the number of holes present in valence band. In the case of pure semiconductor or intrinsic semiconductor, the number of electrons present in conduction band is exactly equal to the number of holes present in valence band. In the diagram, I have shown the covalent bond and broken covalent bond for our convenience. Pure semiconductors are tetravalent, that means valency is 4. So, what happens when a trivalent impurity is added to a tetravalent substance, and what happens a pentavalent substance is added to a p-type semiconductor? So, scientists observed that the conductivity rapidly increases by this phenomena. So, the phenomena of adding impurities to a pure semiconductor is called as doping. The phenomena of adding impurities to a pure semiconductor is called as doping. So, by doping to a pure semiconductor, extrinsic semiconductor can be formed. A semiconductor doped with suitable impurity to increase its impurity is called extrinsic semiconductor. On the basis of doped impurity, extrinsic semiconductors are of two types. One is N-type semiconductor and second one is P-type semiconductor. So, when a pentavalent impurity like arsenic and bismuth is doped to a pure semiconductor, an N-type semiconductor will form. Here the pentavalent impurity is ready to donate one electron, so it is called as donor impurity. So, pentavalent impurities are also named as donor impurity. When a trivalent impurity like aluminum and boron is doped to a p-type semiconductor, when trivalent impurity like aluminum and boron is doped to a pure semiconductor, a p-type semiconductor is formed. Trivalent impurity ready to accept one electron, so it is called as acceptor impurity. There are two types of extrinsic semiconductors, p-type semiconductor and n-type semiconductor. First we discuss n-type semiconductor. When arsenic is doped to germanium, generally the doping is in the order of 1 in 10 power 6 atoms. If doping percentage is 1 in 10 power 6, the conductivity increases by 10 power 6 times. So, when pentavalent impurity arsenic is doped to a pure semiconductor, the energy level formed because of donor impurity is called as donor level. It forms just below the conduction band, just below the conduction band. The energy level formed by the donor impurities just below the conduction band is called as donor energy level. It is very close to the conduction band, and the electron, the fifth electron present in that. So, even though if small amount of energy 0.045 electron volt, that means energy is in the order of 0.01 electron volt, it shifts to that conduction band. So, in the diagram it is clear that the number of holes present in valence band is greater than that of number of holes present in valence band. The number of electrons present in conduction band is greater than that of number of holes present in valence band. Okay. In impure semiconductor, the current is due to both electrons and holes. So, total current I equal to IE plus IH. So, here in n-type semiconductor, the majority charge carriers are electrons and minority charge carriers are holes. So, the energy required to detach the fifth loosely bound electron is in the order of 0.45 electron volt for silicon and for 0.01 for germanium. Okay. The majority charge carriers are holes and minority charge carriers are electrons. In the case of n-type semiconductor, the energy level is also named as donor energy level. So, n-type semiconductor is also called as donor type semiconductor. Carrier concentration in n-type semiconductor. if n represents the electron concentration and P represents the hole concentration, n into P equal to Ni into Pi, where Ni is intrinsic carrier concentration and Pi is also intrinsic carrier concentration, which is equal to Ni square. When the concentration of electrons is increased above the intrinsic value by the adding of donor impurity, and the total factor remains constant, which is equal to Ni square. P-type semiconductors. When trivalent impurity like indium is doped to a pure semiconductor germanium, the 3 free electrons bonded with 3 germanium atoms and lack of electron. So there is energy level formed because of impurity substance, that is acceptor energy level. It is just above the valence band, and when some electron when some energy is given, some of the electron may jump from valence band to acceptor energy level, and if the energy is more, the electron easily jump from valence band to conduction band. So in the case of pure semiconductor, the number of electrons present in conduction band is less than that of number of holes present in valence band. In p-type semiconductor, the current is due to both electrons and holes. A trivalent impurity is called as acceptor impurity. The energy level is called as acceptor energy level formed just above the valence band. So p-type semiconductor is called as acceptor type semiconductor, and in p-type semiconductor, majority charge carriers are holes and minority charge carriers are electrons, and n into p equal to Ni into Pi equal to Ni square. Electrical conductivity of semiconductors, this is important. When some electric potential is applied across the semiconductor, both electrons and holes move in opposite directions. So IH represents current due to holes and IE represents current due to electrons. Both electrons and holes move in opposite directions. Total current in the semiconductor is given by I equal to IE plus IH. And in the case of semiconductor, by applying a small potential difference across the semiconductor, both electrons and holes move in opposite direction. So the total current is given by I equal to IE plus IH. And in electricity part, you have that the formula for IE equal to NeEAV, where Ne is number of electrons, E charge of electron, A area of cross section, VE drift velocity. So from that we can write the formula for total current IE, NeEA into VE plus NHEA into VH. According to Ohm's law, I equal to V by R, and R equal to rho L by A, where rho is resistivity or specific resistance. VA into rho L equal to EA NE VE plus NH VH. and intensity of electric field E is V by D or V by L, and the mobility is defined as drift velocity per unit electric field. The reciprocal of resistivity is called as conductivity. So, the conductivity is given by sigma equal to E into Ne mu E plus Nh mu H. Students, this formula is very useful for the problem solving. The average energy level of conduction electrons and valence band is called as Fermi energy level. In the case of pure semiconductors, the Fermi energy level lies in between conduction band, exactly lies in between conduction band and valence band. In the case of n-type semiconductor, the Fermi energy level shifts to the conduction band, and in the case of p-type semiconductor, the Fermi energy level shifts towards the valence band. This is the brief description of types of semiconductors, and next we move to that very important concept. What happens when a p-type semiconductor and n-type semiconductor is suitably joined? That is the next topic, because in p-type semiconductor majority charge carriers are holes. In n-type semiconductor the majority charge carriers are electrons. What happens when a p-type semiconductor and n-type semiconductor join with each other? Okay students, next class we discuss that is very important concept.